our recording. Okay, welcome to class. I guess it's Tuesday, April 14th. The main point, well, okay, there's two main things we need to do today. One is business related, and one is we need to talk about moments of probability distributions. Business wise, just to review, I'm meeting with the Canopy Waves folks. So that's, I guess, just Blake is the only one here from them at 2 today. Is that correct?
Yes.
Great. And then the traveling sales astronauts. So Josh and Leonard at 3.
Yep.
Okay.
Yep.
And then of course the Galaxy group over on Thursday. Okay, the other thing is abstracts for the poster session. It is still not clear exactly what the format of this thing is going to be. It looks like it may simply be a web page where people can post the PDF of their poster and a video of them presenting their poster. Yeah. This whole thing is going to be interesting, but the relevant piece here for us is that, well, okay, there's a couple of things. One is that the poster session is only going to be available to people. It's going to require a sign-in from a Chico State web account. That's because some of the folks in biology and chemistry are concerned that if they put out unpublished research on this thing, that somebody else will scoop them, meaning will swoop in and do the work for them. This is less of a concern for us because doing the work is hard. That's not to say that it's not hard in biology and chemistry, but in biology and chemistry, you generally have, this like, what's the right word? It's a target-rich environment, right? There are like 10 kajillion molecules you could dream up. And the fact that in chemistry, you spend a lot of your time just trying to synthesize stuff and trying different things, and then being able to say, oh, we found one that's interesting. That's the real thing, right? And so if other people were to see that, they could swoop in, look at the one thing, out of the 700 you tried, and publish it before you had a chance. So they're very concerned about that. So the poster session will not be available to the public. It'll require a Chico State login. Yeah. Okay, on the posters, abstracts are due next Monday by 5 p.m. So what I want to do at the beginning of class on Thursday is go over everybody's abstracts. That means you need to have an abstract by class on Thursday. I haven't checked on where things are. I saw that the traveling salesman group shared a document with me, so that's good. I've got a document from the Galaxy group. Blake, you're the only one here, so it just falls on you. But have you guys done anything with the Canopy Wave?
Yeah, I'll share it with you.
Okay, yeah, that'd be great. Or just throw it on the Slack channel. That also makes it easy for everyone to find.
Will do.
Okay, so and then Thursday we'll go over those. So we'll I'll just have each group go through and sort of present their abstract, and then everybody else can get out there, sharpen their knives and prepare to attack in a very nice and productive way, but just poke it to pieces. And hopefully we'll come out of that with good abstracts where everybody's feeling, like they've got a solid thing, and then we can go ahead and submit them. So we're not trying to do that at the last minute on Monday, because as I mentioned, this whole system is being cooked up at the last minute, and I don't know how reliable it is. So I think we just do our best. Okay, questions about any of that? Okay, just as a preview of what's coming up, next Tuesday, we're going to talk a little bit about posters. And next Thursday, we're going to need a draft of your poster to go over. It doesn't have to be a final draft, but it needs to be started. So that's coming fast. This whole thing is sort of, we're sort of madly barreling to the finish line here on this semester. And so just as a heads up, we're going to need to start putting together posters. That means one of the things we're going to focus on when I meet with you guys this week is what kinds of things do we want to show on these posters? Okay. So with that, Dylan was supposed to have the reading, the section of the reading to present today. As I mentioned, he's not going to be able to join us. So he's going to go on Thursday. For Thursday, I'd like you to read 3.3. And don't worry too much about it. It goes through a lot of detail about what it calls characteristic functions. They're just the Fourier transform of the probability distribution function. That's all the characteristic function is. It's the Fourier transform of the probability distribution function. But do have a read in 3.3. We'll go over that a little bit in class on Thursday, and Dylan will be in charge of presenting that. Okay, so let me talk just a little bit about 3.2. So let's see here. I need to, hold on. Okay, can you see that?
Yep.
Okay, so section 3.2, if you've had quantum, this will seem very familiar because it is exactly what you do in quantum mechanics. In quantum mechanics, we call them expectation values. In statistics, they call them expected values, but it's the same general idea. The idea is that you have some distribution, and you're going to calculate relevant quantities. In quantum mechanics, they're physically relevant quantities. In statistics, they're descriptive quantities from that probability distribution function. So you should have realized by now that your probability distribution function, to take the analogy from quantum mechanics, is just the wave function. It's psi star psi, right? It's the wave function times its complex conjugate is a probability distribution function. And because most of the stuff we do in statistics are real values, that simplifies things a little bit, but it's the same general idea that all we're going to do is calculate the expected value, right? So if you look on in section 3.2.1, it says what an expected value is, right? And they use this notation. Hold on, let me turn on this thing. They use this notation. They'll use the two notations interchangeably. One is the capital E, right? And the one that's really interesting to look at is the continuous distribution, because remember, you can make any discrete distribution into a continuous distribution if you just make it a bunch of delta functions added together. So this continuous distribution, the expectation value of some function of x is just the integral over the entire range of that function of x times your probability distribution function, and you just integrate the whole thing, and out pops your expectation value, okay? So they go through a few basic principles. It's a linear operator, so it obeys all the nice rules of linear operators. And you can't, right? These first two are sort of the same statement, right? The expectation value of a constant is just a constant. The expectation value of an expectation value is the expectation value, which is the same statement because the expectation value is a constant. It also gets into a little bit talking about independent variables. We'll get into that a little bit more next time, and actually we'll really get into that next Tuesday. The other thing that they have here is that this expectation value is often denoted by these angular brackets. Again, for those of you with in quantum, this should look very familiar, right? Just put u, instead of u here, have a psi and then a bar and then a psi, and you've got a wave function, right? So it's the same general idea. That's why the bracket notation in quantum mechanics exists the way it does. Okay. And it's important to note that for nonlinear functions, you can't just put the expectation value into your function and get out the expectation value of the function. And it goes through a bunch of different examples, right? So for example, it talks about they've got some kind of detector that gets the momentum of a charged particle where the momentum as a function of charge is equal to 1 over the charge. And so you can go through and figure that out. And what you find is that it's not simply, you can't simply say it's just the expectation value of the chart of 1 over. And so, it goes through the example and shows you blah, 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 blah. The important thing here is looking at a few different moments that are generally important. Two of them you already are very familiar with. One is the mean, right? You've all been taking means of distributions without even knowing it for a long time, right? And the mean for a continuous distribution is analogous to the center of mass. The center of mass is the mean for a continuous distribution of mass. And the same way they have examples of other things, they have examples for different distributions. The variance is the expectation value of the variable squared. And generally we define it as the variable minus its mean quantity squared. That's simply to make it so that it's directly comparable if you shift the distribution over to the left or right by changing the mean. It goes through some properties of it, right? The variance, that expectation value up here, is the same thing as the expectation value of the distribution squared minus the mean squared. And it goes through some examples here about variances. Variance is, of course, really important from a statistical sense because it is the uncertainty, right? It's what we report when we talk about the uncertainty on a measurement, okay? And one of the things they do here, and I won't go through it, but I'd encourage you guys to think about it, is this thing where they talk about the variance of the sample mean. So basically what this is showing is that your variance is going to, for some distribution, is going to drop as you take more data. As you take more and more data, right, it's going to drop, the variance is going to drop like 1 over the number of data points. I'm sorry, the variance of the uncertainty, maybe is a better way to state that. The variance on the mean that you calculate is going to drop as you take more data. That essentially just simply means that you know your distribution better as you take more data, which is not surprising. But if it's random data, right, if it's not not correlated in some way, right? If each data point is an independent measurement, then that uncertainty is going to go down like 1 over the square root of the number of data points. So this is kind of the experimental way of just beat it to death with a hammer, right? You can just always get a more accurate result if you just take a few more data points. Okay, the last two, which it does not spend much time on here, but are interesting and useful to talk about, are the skewness and the kurtosis. Skewness is exactly what it sounds like. It's the asymmetry of the distribution with respect to the mean, okay? And the kurtosis, or what's more usually calculated is called the excess kurtosis, essentially tells you the relative size of the tails of the distribution compared to the center of the distribution. Okay, so let me see if I can sketch this. Let's see here. I should be able to stop sharing that. And okay, I'm just going to share a whiteboard. I'm going to try to write this with a mouse, which will mean it looks ugly. So let's suppose I have a distribution, right? And if it's a Gaussian distribution, it just kind of looks like that, right? I can imagine making a distribution that instead of looking like a nice Gaussian, right, that does this like exponential fall off towards the edges, I could make a distribution that looked like this. And if I had drawn this right, it could have the same total area, it could have the same mean, and it could even have the same standard deviation. Both of them are symmetric about the center, so they'd have the same skewedness, but they're very, very, very different types of distributions, right? The boxy one, if you were, say, investing people's money, right? The boxy one would be much more comfortable for people because while they aren't going to necessarily know how things are going to go, they know it's not going to go really poorly. They also know it's not going to go very well, but it's safe, right? Whereas the Gaussian distribution has a chance, not a big chance, but a chance that, you could lose all their money, or a chance that, hey, they could become millionaires. So the kurtosis basically tells you what are the chances of an extreme event relative to a Gaussian distribution. So does that make sense? Okay. So the idea here is that what kurtosis measures is the likelihood of extreme events, okay? And then it goes through some examples. What I want to do as sort of our example here is to calculate the moments of oh, by the way, the mean, the standard deviation, the skewedness, and the kurtosis are often referred to as moments of the distribution, okay? They are the first, second, third, and fourth moments of the distribution. Because as was shown in the text, they are all related to the expectation value of your either x or x squared or x to the third or x to the fourth. Okay, so what I'm going to do here is I'm going to share, hold on one sec. I'm going to share my screen again. I want this guy. Okay. And so we already actually calculated the mean. But we calculated the mean in sort of a normal way, right? We just added up all the values and divided by the total number. What I want to do is instead calculate the mean of our distribution using the probability distribution function. So I'm going to come down here and I'm going to add something. Calculate mean, variance, skewedness, and kurtosis. Okay. By the way, if you want a really fun vocabulary word that almost nobody knows, a kurtosis smaller than a Gaussian is called a eukurtotic distribution. And so, that's a fun word, eukurtotic. Write that one down. Use it in a paper. I once I used that in a paper I wrote a number of years ago, and I actually got a comment back, not from the referee, but from the editor, saying that that was a new word for them, and they had to look it up to make sure it wasn't just garbage. Okay, so we're going to calculate these things, okay? And we're going to do it using the probability distribution function, okay? So if you remember from up here, this is for our Monopoly setup. We grabbed out the probability distribution function, and we know the bins, right? We know the X values that they go along with. And so we can calculate the, I'm going to call it the mean move by just taking we want to take an integral, right? Which in this case is just a sum. So we're just going to do a sum of our bins, our roll bins. And if you remember our roll bins, there are too many of them. So we have to go all but the last one, right? Times our PDF, right? And this would just add up the sum. Our PDF is normalized, and that should give us the mean. So if we come over here and then we print it, mean, and we're just going to print our mean. And that should be the same as our average that we calculated the normal way. And if we go ahead and do it, we'll find that our mean was 8.33. And I didn't print out our average, but we can come over here and check it. And sure enough, it is the same as our average move. Our average move is 8.33. Our mean is 8.33 spaces. So when you roll the dice, when you take a turn in Monopoly, on average, you're going to move 8 spaces, right? 8.33 spaces. Okay, that makes sense. Now let's calculate the variance, right, in this same way. So our variance for our move, right, is just going to be the sum of, and remember, we're going to take the exact same thing we did before because we're just taking an integral, right? But now, instead of just taking the rolls, we're going to do the rolls minus the mean, and we're going to square it. And then we're going to multiply by the PDF and add it all up. Okay? Does that make sense? Okay. It's not the way we traditionally talk about doing this, but it actually is the same thing. It will produce the same result as our normal formula where we just take all the data. Okay? And if we want to print this thing, right, we're going to do basically the same thing we did before. the variance is going to be our variance move. We hit go, and we get that our variance is 17.42. Now, scientifically, we usually don't report the variance. We report the standard deviation, which is simply the square root of the variance. So we could come down here and say that the our average move is our mean move plus or minus the square root of our variance. And if we ran the thing, we would get this idea that on average, each turn in Monopoly, you're going to move wait, why is that different? Why did that change? Weird. Oh, because the data changed. I'm using random data. Okay, so even though I'm using 100,000 data points, it changed by 200ths, right? Okay, so our average move is 8.3, 8.4 spaces plus or minus 4.2 spaces. Okay, is that actually true? If we go back and look at our distribution, if I go, so there's my mean, right? So if I go back 4.2 spaces, right, that's going to be roughly 4. So that's going to be right here. Okay. If I go forward, that's going to be, close to 13, 12 and a half. That's right up here. Is that actually right? Do you have an equal chance of going more than 13 spaces or more than 8.3 spaces and less than 8.3 spaces? Or let me put it this way. Is it equally likely that you will go 13 spaces or 4 spaces?
No.
No. And this is where we get to this concept of skewedness. This is a skewed distribution, right? So the mean is telling you the average, right? And the variance is telling you how much it's likely to change around that. But it doesn't tell you which direction it's likely to change. So we need to calculate the skewedness. So to calculate the skewedness, we're going to have to do the third moment of the distribution, right? And formally, the skewedness is defined as, well, here, let me just copy and paste it. We divide the skewedness by the standard deviation cubed. And all that is to make it unitless, okay? So we're going to divide it by the variance to the 3/2 power. 3/2 power. And I'm just going to put this whole thing in parentheses so I'm not screwing it up. Okay. So, and I want to take the third power of the value minus the mean. And now we're going to come down here and print it. So looking at that distribution, which way is it skewed?
Right skewed.
So in other words, it's, oh goodness, I'm having a hard time. So in other words, it's more likely to get a bigger number than a smaller number, right? the distribution is weighted towards the right, the positive end, right? The high end. So that means we should get a positive skewedness, okay? Skewednesses can be positive or negative, right? Because you've got a third power there, just like means can be positive or negative, but variances and standard deviations can't be because you have even powers. So if we calculate this thing, we get our mean is 8.3 still. Our standard deviation is 4.1, 4.2, and our skewedness is 1.8, okay? What that means is if we come over here and we look at our distribution, there is the tail over here is much bigger than the non-existent tail over here. And so it's a skewed distribution, right? There is a much bigger tail on the positive side of the distribution, the high side of the distribution, than there is on the low side of the distribution. Okay, how about the last one? Kurtosis, which is just fun to say. Any guesses? Let me put the thing back up here. Any guesses as to what this distribution is? Is it going to have a kurtosis greater than a Gaussian or less than a Gaussian?
Probably greater than a Gaussian.
You think greater than? Why?
Well, because the tail, well, I mean, it does have a long tail on the right, but there is no tail on the left. So it might, I mean, it's hard to say, actually.
It is actually a little tricky. It helps a little bit if we look at this in a log, right? Because in a log linear graph, a Gaussian should look like what?
Well, it should just look like linear on the edges, right?
Linear? A Gaussian has an x squared, right, in the exponent. So this should look like a parabola.
Oh, right.
Well, this side maybe does kind of look like a parabola, right? But this side doesn't. So we'll see. We'll see. Kurtosis is one that I have a hard time just guessing off the top of my head what the kurtosis is. The kurtosis is defined as simply the fourth moment, right? So we just do the fourth power here. We divide it by the variance squared. And then usually what's actually reported is that -3. And the reason for that is because a Gaussian, this formula, if you plug it in for a Gaussian, you get 3. So if we subtract 3, then if you have a positive kurtosis, you are what's often called an excess kurtosis. You are more likely to have extreme events than a Gaussian. And if you have a negative excess kurtosis, you are less likely to have extreme events than a Gaussian. So if we go ahead, I need to add the print thing. And our excess kurtosis is the kurtosis of our moves. And if we go ahead and run this thing, we see that our excess kurtosis is 4. That means that it is much more likely that we will have extreme events far from the mean, than we would in a standard normal distribution, okay? And the reason for that is what Bjorn was actually saying. If we come back over here and look at this as a log distribution, again, the reason here, this is actually falling off almost like maybe a quadratic, but there's a huge deficit right here. Can you see my, you probably can't see my pen. Let's try that again. There's a huge deficit right there, right? And so you have this sort of Gaussian-like core here that's falling off, right? That should fall off like a parabola, but that parabola should fall like down this way. And so you have this big excess over here. Okay, if you're designing a board game and you want it to be exciting, you want this kind of a distribution. Why?
So people feel like they have a chance to roll really high.
Right, because if you want to make an exciting board game, right, you want to give people a chance, not a very good one, but a chance for something really dramatic to happen, right? Big swing, things just went crazy. All of a sudden, wham, everything changed. Those dramatic swings are what make board games often very interesting. Now, what it also means is that it's more dominated by luck than it is necessarily by, somebody's got arrows. Okay, he's putting arrows all over my screen. All right, nobody's willing to admit their arrows. I didn't know you
Sorry,
could
I
do
didn't know
that.
you could see that.
Is it a stamp? Oh
Yeah, it's a
there you
stamp.
go. Cool. I can put arrows all over. Hey, look, arrow.
Hey, hold on.
I didn't know that was a thing. Can I erase other people's arrows? Hey, look, I can erase your stuff. Go away. Ha. Cool. All right, sorry, that's completely off topic, but I didn't know I could do that. I didn't know you guys could do that.
I didn't know we could do that either, frankly. I thought that was you, Nelson.
Okay, so anyway, the point here is that we've got to we can calculate these moments of the distribution, which give us a statistical way to describe the probability distribution function. Okay, for a Gaussian, all higher moments of the distribution are 0, right? So the 5th moment and the 6th moment and the 7th moment are 0. That is not true for other distributions, but it gives you a interesting reason why the Gaussian distribution is the one is so commonly used, because it turns out that it's fully described by just 2 numbers, right? Just the mean and just standard deviation. Okay. It has no skewedness, it has no kurtosis, no excess kurtosis, and everything else higher than that is 0 as well. Other distributions are going to have other values, right, for these moments. Okay, so the point of all this is you guys learned when you were kids all about mean and standard deviation, right? And you learned about them using these really cumbersome formula that didn't seem very arbitrary, okay? Hopefully they seem less arbitrary now. All they are is they're related to moments of the distribution, right? Expectation values in the terminology of quantum mechanics. The expected value you would get out if you looked at just the roll of the dice, or the range of rolls of the dice, or the skewedness of the rolls of the dice, or the chance of extreme values in the rolls of the dice. Okay, questions? All right. Then we will stop there. Please remember to get cracking on abstracts. Share those around with the members of your group. And we'll talk about them a little bit when I meet with the individual groups, and we'll go over them on Thursday.
Sounds good.
Okay.
Alrighty.
I'm going to turn off the recording here.
Sorry I'm late, Dr. Nelson. My computer did not want to start up this morning at all.
That's okay. You are looking a different color than you used to.
It's the lighting, honestly. No,
But some pretty dramatic lighting.
So I tried dyeing my beard blue because we're in quarantine and nothing matters, and we just got graduation canceled on us today. So
Yeah, I saw that.
yeah, so that'll be fun. But yeah, the first time I tried dyeing my beard blue, my beard was very dark. So we realized, hey, I need to do something to get it lighter so that the color will actually show. And here we
There
are.
you go.
Alrighty.
Okay.
So the real question is, when will we get to see it blue?
Yes. That probably sometime today. All I got going on today is desperately trying to catch up on my grading for ARPAN. I haven't even, and that's just like the homework that I've had before spring break. So I have all the stuff that I had before spring break and all the stuff that has been turned in since. And I still need to email Dr. Buchholz about getting my incomplete. And which I have a draft. I have a draft. I'm just like, oh, I need to send this. Oh, I need to send this. But I want to make sure that it's like appropriate, yada yada. I think I'm just going to reread it once and hit send. Rip
That's
the
my
Band-Aid off.
recommendation. Sending anything at this point is probably better than sending nothing.
Ain't that the truth?
Because in all seriousness, I don't know how the graduation process works, but I would not count on the bureaucracy running efficiently for anything at this point. I mean, everything is just gummed up, right? They just send out a big thing to faculty, basically trying to figure out how to make sure we can all get like pens and whiteboard markers at our houses, which, would have been a thing that some of us were clamoring about like a month ago. But, it's hard, as it turns out, to shut down the world. So
It's the end of the world as we know it.
I also received official word yesterday that my REU will be going entirely virtual.
okay, but they're still going to do it.
Yes, they are, which I am feeling very, I feel very lucky in that aspect because I know most of the other RUs have just been straight up canceled.
Yeah, well, good for them. That'll be a tricky situation to try to do it all virtually, but at least they're not just throwing in the towel. So
Yeah, I think it's just mostly because pretty much everyone's project is going to be computational. So, as long as people like they sent out like surveys making sure that like people have like, like access to computers and, I don't know what the requirements for the different projects are, but mine, like, I don't need any kind of crazy, like intensive computer. Like I can just use my own PC to do the project.
Okay. I suspect I'm interested to see how it turns out, but I suspect what'll probably happen is that so CU has a in-house supercomputer, and I suspect what they'll probably do is just give you access to that. It's designed to be used remotely anyway, so it's it's nice.
Yeah, I also know for my project actually, Dr. Erickson is going to just mail me a hard drive with all of his data on it, because basically he just has a giant mountain of data from like 10 years of satellite data basically. And it's
Okay, it's
basically just,
satellite.
yeah, so it's milling through it and attempting, it's like what I'm going to be trying to do is like maximize like the number of magnetic reconnection events that you know can be like detected from the data. And he's already found a lot, but basically I'd be trying to optimize that search.
Cool.
And so
Well,
that'll
that sounds
probably
like
be
a
the
good
first part of the
project.
project. Yeah.
Where are you doing your REU, Bjorn?
So I was going to do it at LASP in Colorado Boulder, but now I'm doing it at home. The cool thing is they did say that they would be like reserved, like they do provide like a travel expense, which we're not going to have to use, but they said they can reserve it. So sometime like later in the year, we can all like take a visit to Boulder. So getting to at least visit would be cool.
Yeah.
Go you, bro.
Good.
Is it
Okay.
bad that I've kind of wanted to start reaching out to some of the grad schools that have rejected me and been like, hey, the plans change? Like, you guys need a body in your program now? Like, I'm still available. Like, but yeah. So that'll be fun. Go you, Bjorn.
That's exciting. All right. Well, I'm going to jump off and I will see you guys later.
All right. Take care, Dr. Nelson.
Oh yeah. Also, Sean, do you want to